This is Off the 11th Hour, and I'm your host, Nathaniel Stone, but we all know who the Lord of Hosts is. Say it with me in any dialect you so choose. Yahweh, Sabaoth. Kodesh brothers and sisters, fellow members in the body of Messiah, and those in the world, thank you for giving me your attention in a world full of distractions. Actually, I've been wanting to do this episode for a while. I'm really excited to do this episode. As some of my listeners may know, I am in school, and I am taking a physics class, and we had to do a final project, and we were given some leeway to do a final project, and I asked if I could talk about the subsolar point and some other calendar-related issues, and my professor allowed me to do that, and so that I can go ahead and use it as a presentation on my channel if I wanted to, so that's what we're going to be going ahead and doing. I'm glad to have this project, actually. I have been sitting on some material since 2020. I have so much to do, and I don't have enough time to do it in, and I have been wanting to do this regarding calendar. The episode here is called Calendar Confusion. In order to understand the calendar, you need to understand how essentially the clock works. So the point of this is basically to explain how the clock works. So I'm going to quickly get into some a topic of why we need to be studying the clock, essentially, the grandfather clock in the sky. So in Genesis, on the third day, Genesis 1:14, he says that there needs to be, the fourth day, at the end of the third day. At the fourth day, Elohim, that's a Hebrew word for God, said, "Let lights come to be in the expanse of the heavens to separate the day from the night. Let them be for signs and appointed times and for days and for years." And then verse 16, "And Elohim made two great lights, the greater light to rule the day and the lesser light to rule the night, and the stars." So there's a lot to unpack. I'm not going to be able to unpack everything. Maybe in future episodes I'll have time to go over this in more detail, but I'm going to give just some of the answers here. The greater light to rule the day is the sun, and the lesser light to rule the night is the moon. They are the two big, lights in the sky, and the stars. And he says here that they are for, in verse 14, that they are for signs, appointed times, for days and years. So essentially they are timepieces, the grandfather clock in the sky. The word here for appointed times in Hebrew is the word moedim, or moed in singular form here, as you see here, moed in Hebrew. And this would basically be holidays, the holidays. They're for holidays, essentially to know when the holy day is. And so essentially that these lights are to help us to understand the timepiece of not just days and years, but also to know when the holy days are, and also for signs. This word for sign is oath, and it is a beacon, a monument, an omen, a mark, a token. Essentially what I would say is that, even though it does say sun in the scriptures, and it does say moon in the scriptures, right? The word for moon is Yarach, and it does say year, Shemesh, in the scriptures. Those are just words, and we need to take this understanding from words and apply it into our daily life. So, that's the one thing that I see of those in this community that are doing wrong is they are essentially only studying, when studying things like the calendar, they're only studying things directly from scripture, and they're not applying it out into our world. And we're going to get more into that here in a little bit, but essentially it's for studying in order to know, what makes a day, or what makes a month, or what makes a year. What makes a week. You need to have an understanding of the demarcation points that are there. We're going to get more into that here in a moment. But I want to say that an example was set by Daniel. Daniel here 1:4, that he was given knowledge and understanding. He was learning, basically he went to Babylonian college is essentially what he did. He was taught the writing and speech of the Kasdim, the Babylonians. And here at the end of the verse, it says here that any word of wisdom and understanding about which the sovereign, the king, examined them, he found them 10 times better than all the magicians, the astrologers who were in all his reign. So these astrologers or these magicians, these soothsayers, these people, Daniel was 10 times smarter than these astrologers. Daniel understood how the calendar functions on a deep level. A lot of people will say that, or there's a common understanding is that the Magi, when Christ was born, and they saw the signs, the Star of Bethlehem, and they were reading the signs in the sky to know that this is when the Messiah is going to be born, that they learned from a school that Daniel established. They essentially are through the generations, students of a school that Daniel established, as he passed on that information. So I have a lot of information to get into, so I'm going to get on my whiteboard. And I'm going to write here. Hopefully that's not too big. That's a little bit big. Let me make this a little bit smaller. I'm going to write here day and month. We're going to be getting into the subsolar point in a moment. And year. Now the patterns between a day, a month, and a year, we're gonna draw 3 circles. As we know that a day is cyclical, right? It resets. A month is cyclical, right? You have the first of this month, the first of the next month, and then you have the same month but the next year. So all these things are cyclical. And what I'm going to show here is that a day, a month, and a year are essentially have the same pattern. So if you're going to ask yourself, as far as a day goes, what are the special points in a day that are unique unto themselves in the cycle of a day? Gonna give a moment to think about that. But there are 4 demarcation points. 2 might be easy to see right off the bat. Right, we have sunrise, or I'm gonna put this in SR, sunrise, and then we have sunset. I'll put that over here in SS. Because this is when the sun is right at the horizon, but it's rising. So it's essentially half light, half dark. It's the demarcation point of light and dark, but it is rising to a point. And then here at sunset, it's half dark, half light as it is setting and going in this direction. So, a quarter turn from those, you have the most amount of light, and we're going to call that high noon. We'll just right here noon. And then the opposite point of that we have is midnight. I'll just put MN here for midnight. So essentially we have the most amount of light in a day, the least amount of light in a day, half light, half dark, rising into light, half dark, half light, descending into darkness. It's that pattern that is there. And then essentially, if this is the cycle of a day, we have to pick where in the day do we use. Now, the Gregorian, we reset, or the America resets the day at midnight. That's when the day shifts over. But the Hebrew understanding of when the day resets, there's a big debate on it. And I'm not going to get into why I've come to this understanding. I'm just going to give my answers to move forward. And in a future episode, I'll get into it. A day begins at sunset. That we have. So the day essentially ends, when the sun goes down. There came to be evening, there came to be morning the first day. There came to be evening, there came to be morning the second day. The way I see it is that there came to be evening and all the period and time between that. There came to be morning and all the period and time after that of first day. And then the next evening marks the cycle, again. So in month, we have that same pattern. We have those same 4 points that are there. So as far in the Hebrew word, I should say, in the Hebrew understanding, it's actually where the word month is derived from. The Hebrew understanding of the month, it comes from the moon, the munth, right? That's kind of where this term came from. And the scriptural understanding is that the moon controls the cycle of the month. There's a debate on that also. I'm not going to get into every point of why I have an understanding that the month is controlled by the moon, but the common consensus and the majority of people that are following the Hebrew calendar do believe that the moon controls the month. So as we get into that, what part of the moon is unique and that is similar to the parts of the day? Well, here we have, we'll call it a full moon. We'll call it FM for a full moon. And then down here, we have a new moon, NM. So it's essentially the most amount of light in the cycle, and there's the least amount of light in the cycle. And then here we have it's a 1/4 waxing. And then over here, we have a 3/4 waning that is there. And so what we have is a very similar cycle, is that the 1/4 wax is similar to the sunrise, because it is when the moon is 50% light, 50% dark. It's the line of demarcation. I think I have one over here. Yeah, like this. Depending on where your location is at, it could also look like this here. Well, that's the same thing. Yeah, sorry. But yeah, here, let me kind of get one of these here. I have these for later on, but I can pick up this, and essentially it would be like that. There we go. So you would have a 1/4 waxing and a 3/4 waning in the cycle of the moon that is there. Then the next thing that we have is the year. So what 4 parts of a year, and this is the part that we're going to be focusing on, what 4 parts of a year are unique to himself but have a similar pattern to the month cycle and the day cycle? Well, we have the equinox, and we're going to call this the spring equinox. And we're going to call this the autumn equinox, and we'll get into what equinox means here. And then we have the summer solstice, and then we also have down here the winter solstice. And so the summer solstice, well, let me get rid of that there. The summer solstice is the most amount of light in the cycle of the years, the longest day of the year in the northern hemisphere, and then the shortest day or the longest night of the year occurs at the winter solstice. And we're going to get into what makes a solstice, what makes an equinox, and what makes our calendar that we're on today. But to show you kind of here, we have the day, the month, and the year, and essentially the patterns are the same. So therefore, noon on the day, the most light in the cycle, is similar to a full moon on the month cycle, and it's similar to the summer solstice on the year cycle. Like a autumn equinox is a 3/4 waning, is a sunset, or a sunrise is a 1/4 waxing, is a spring equinox. You see how that pattern works. So Hebraically, we need to figure out, what is the demarcation point of a moon? Basically, when do you make the ticker on the moon? The moon. A lot of people, they use the crescent moon, or they'll use the new moon. So we'll just kind of I'll draw a little bit of a larger circle here, but it's in this area here. It's another video that we'll talk about. Always debate points on every interpretation in the scriptures. But what makes a year, and what is the point on the year that we are using? And so according to the scriptures, talks about Passover in the month of Abib or Aviv, depending on your dialect that you're using there, and it puts spring as the demarcation point when the year resets. So, with that being stated, let's look at some calendar confusion that we have in the world today. This is a website. I'll put the link here. This is Wikipedia on Gregorian calendar. And the problem is a lot of people, they may or may not know the calendar that we're on. We are on the Gregorian calendar. It is named after Pope Gregory the 13th. When he reset it, and he reset it from the Julian calendar. So the scientist here, Lilius, was proposing how to fix the problem, and the problem is that the Julian calendar, Julius Caesar, the Julian calendar is about 11 minutes longer than the mean tropical year. You might not know what tropical is. I will explain that here momentarily, but he is saying that essentially every year it's 11 minutes longer, and what that comes out to is it's about 3 days every 400 years. And so in the 16th century, the 1500s, the dates were not lining up, meaning that the demarcation points of the winter solstice, the summer solstice, the equinoxes, vernal and autumn were not lining up, and they were off by about 10 to 11 days is about what they were off. Here it was 10, and then the following century was the 11 days. So here at the website say it was a 10-day correction, and then the year later, the century later, when the rest of the world adopted it, it was 11 years off by the time that they fixed it. But there was they needed to correct the calendar, and so what they did, the Julian calendar says that there's 365 in even quarter days in a year. Well, there's not, because Lilius, he gave an average here that there's 365.2425. So it might not seem like a lot, the accuracy of 0.25 or 0.2425. But, again, over time, there was a large discrepancy, and 1600 years later, there was a 10-day correction that needed to be made. So what they did to fix it on the Gregorian calendar, now a lot of people, they're like, well, a leap year is essentially an extra day every 4 years. And they're mostly correct on that. But that's actually what the Julian calendar, that's the error of the Julian calendar, is they just did an even 1 day every 4 years, but that's not what it is, and this is what caused the discrepancy. So what they propose is that how did they word that? They worded it that a leap year is divisible by 100, but also needs to be divisible by 400. So essentially, like the year 1900. So the year 1900, well, if you divide that by 100, you get 20. And then 20 divided by 4 is an even 5. But if you take 1900 and you divide that by 100, you get 19, but 19 does not divide evenly by 4. You're left with 4.75. Therefore, that's not able to be a leap year. So that's why the year 2000 was a leap year, but the year 1900 or the year 1800 or the year 1700 was not. But the year 1600 was. Essentially, it cuts out three leap days every 400 years. And this was enough to fix the problem. However, the issue is that it's still not perfect. And the reason why is because, according to the scriptures, the day or the time is not connected to calculations of man. So I'll give you something interesting here. This here is going to be an hourglass that is there. And as we know from an hourglass, it's filled with sand, and then it drains down and then fills up in here. So what an hourglass does essentially is it is a way to tell time, because they figure out how many grains of sand can fit through here every period in time, and then when you get accurate enough, they can figure out how big to make the hole, how many pieces of grain of sand to put in there, how large to make the glass, and then they're able to essentially come up with an hourglass that is there. Well, the word hours in our English language today is an anagram for Horus, is what it is. Horus was trapped in the sands of time, and his life was connected to the sands of time, and he was going to die unless he could figure out how to stop time. So what he figured out that he could do is, let me get this rotate here. When he figured out that he could do is he could turn it on its side, and then essentially it would stop the grains of sand from falling, because gravity comes down. So all the grains of sand, move down here. So time stops. And so that's how he was able to defeat that, that trap that he was in. And this is actually where we get the infinity symbol today. The infinity symbol is essentially the Horus hourglass of making time infinite by turning it on its side. But the problem with this is that it's super pagan. Is according to the creator, the time is not connected to calculations. Time is connected to the timepiece in the sky, whether it's the day for the sun or the month for the moon, or the integration of the moon and the sun collectively as a year, is that it is time is determined by the positions of the sun and the moon in the sky, essentially. And we see that in Joshua's day, when the sun and moon stood still prospectively in the sky, or in Hezekiah's day, when the sundial, when the shadow went back, meaning that the rotation went back, even though there was essentially more calculated time in that period. A day is from demarcation point to demarcation point, from sunset to sunset. So if the sun stops in position of the sky, and it just stays there, then essentially, even though time continues, the day is longer with, a calculated amount of time, more things in it, but time is not connected to a calculation. And today we do the same thing. We have an atomic clock, in Denver and all other places, and it essentially figures out a decaying particle, and it's calculating nanoseconds, and then it counts those up, and that's how we determine time. It's just a very much more accurate infinity piece. Time glass and hours glass. It's just a very more accurate rebellion against time that is there. So let's get into what makes the tropics and what makes the equator. A lot of people may not know this. It's a very interesting point. I love this topic, by the way. Obviously, that's why I picked it in my project. So I'm just going to draw, not to scale, I'm going to draw the sun. And so we have the sun here, right, giving light. And the sun, the sun comes down to a point. So however big the sun is, right, however big that sun is in reality, eventually there is a center point to the sun, a center point to that light. And that center point to the light hits a spot on Earth. Now, it is always there. And, some people in the community, they believe that the Earth is flat. But if you did flatten out the globe, you would see an image that looks like this. And it's the point, the subsolar point is the point in the sky that the point on the ground that the sun is directly above you, is directly overhead. So as we know, if the sun is here and it is casting its light down here, and we have a pole that's over here, well, the light of that sun hits that pole, and what it does is it casts a shadow from the pole, and we see the shadow of that pole here. I kind of made that a little bit sloppy. Let me clean that up a little bit. It casts a shadow down here. The pole casts a shadow, and then we see that shadow on the ground from the angle of the sun. But if can I do that? No, I can't do that. Let me put that back. I can do it this way. But if that pole is directly overhead in all directions, and it's completely directly overhead, then there is no shadow that is cast for that moment in time. And that is the understanding essentially of what the subsolar point is. And so the subsolar point is always somewhere on Earth, and it's all, unless there's clouds or there's something obstructing it, it's always visibly seen. And so if you were in a spaceship and you were tracking the subsolar point in real time, and you were moving along with it, as we know, as the Earth is rotating, and is rotating this direction, and you were to move as the Earth is rotating, what you would see in a given day is it would track along that path. And the next day, it would track along that same path, but it would be just a little bit higher. And then the next day, it would be just a little bit higher. And let's go by months, and the next month, a little bit higher. And then the next month after that, a little bit higher, until it reaches a certain point. And when it reaches a certain point, it gets as high as it's going to go, and then it starts moving down again until it reaches the lowest point, until it's going to get as low as it's going to go, and then it starts coming up again. So if we're going to use this yellow line that you can see as a 1 day path of the subsolar point, and we're going to fast forward it through time, what we're going to see is right here, this is the summer solstice. This here, now it's heading south. It would be the fall equinox. It's coming down here. It would be the winter solstice, and on its way back up, it would be the spring equinox. So you have, spring, summer, fall, winter, spring, summer, fall, winter, as it's rotating like that. And what it really looks like is if we're going to flatten it out, let's go ahead and flatten it out. If we're going to flatten it out, it would look like, it's kind of difficult to see. I'm going to make these lines a little bit easier to see here. Nope, not that. So this is going to be the equator. And I'm going to do the best that I can do here. And we're going to go ahead and make, this is not necessarily accurate as where the tropic lines are at, but we're going to make that the Tropic of Cancer, the southernmost point, and then we're going to make this the Tropic of Capricorn, and I don't think that that's correct as far as it's not an accurate representation, but it's good enough for visualization right now, because the The Tropic of Cancer doesn't touch that high, I don't believe. Let me see here. Oh, yeah, so kind of right through Mexico City. And we're kind of right through Mexico City, so I guess it does. Okay, so I guess we'll go ahead and use it. I guess it's fairly accurate. Okay. So if we're going to track it throughout the year, and you can watch this in real time, we're going to start from the equator. As we're going from the equator, and we're going to be going in. So that would be from, let's call it spring. And now it hits this topmost point here. And then once it hits this, it's now going to wind. I'm going to use a different color. We'll do blue. And then once it hits a certain point, as high as it's going to go, now it starts winding back out. And now it hits the fall, the equator, which would be the fall of the fall equinox. And then it's going to continue to wind out until it hits the southernmost point on the Tropic of Capricorn, which would be the winter solstice, and then it's going to be starting to wind back in. I'm not sure if you were able to really track with that, but essentially what it does is it looks kind of like a screw. Essentially, it looks like it's like threads on a screw, and it winds all the way up until it reaches the highest most point, and then it winds all the way down. And so the subsolar point and its relation to Earth, it is always changing, but it is the subsolar point that makes the tropical zone and the equator. And so what they do is when you can, and this is not something that's a conspiracy. It's not something that is, NASA definitely lies, and the government definitely lies, and they lie about a lot of things. But this is something that can be visually seen by every single person on the planet. And there are apps and websites, and you can go figure out where the subsolar point is going to be on a given day and go fly there and go stick a pole in the ground. And then you'll notice that on true noon on that particular day, there will be no shadow in any direction for only that period in time. And so the subsolar point essentially is what makes the tropics. Because, am I on a different pen? Oh, there we go. That's why. It's like, there we go. The subsolar point is what makes the tropics. And if you were to follow it, the subsolar point winds all the way up, and it goes north and north and north and north and north until it hits a certain point, and then it comes south until it hits the Tropic of the bottom, the southernmost tip of the Tropic of Capricorn, and then it starts going north again. So if you were to look at it like this way, the subsolar point will be traveling this direction until it hits summer for northern hemisphere people, and then this direction until it hits winter. And then it would be headed this direction till it hits summer. So two complete circuits, one all the way north and then one all the way south, makes a complete year. And they call this a tropical year. And this is essentially what makes the seasons. This is what the plants go by. The plants, they don't have a Horus glass. They don't have the atomic clock. The plants have an understanding of time by the angle of the sun in their given location of where they're at. And so depending on if they're, in a temperate zone or a tropical zone or a jungle or a desert or wherever they're at, the plants know from the position of the sun what time of year it is. So they need to know whether they need to, close up and prepare for cold weather, or whether they need to open up and prepare for spring rains or something of that degree. And so the plants follow the the tropical year. Now, there's a few different ways of understanding a year. There's also another timepiece of counting a year, and it's called a sidereal year. Now, a tropical year is essentially however we however we decide to mark it. So we're just going to draw the cycle, the circuit of a year. We'll go ahead and call this like spring, and we'll go ahead so that when the subsolar point touches a location, we'll call that a demarcation of when it touches a certain location, and we're able to measure that through shadows and poles. We don't need anything really that fancy in order to measure it. And the cycle that it takes to go and make a pattern all the way around until the shadow is precisely even again in that 1 year later, that is called a tropical year. But there is another way of counting a year, and it's called a sidereal year. Now, the stars are very far away. And so this here is going to be a star, and we're going to have our sun here, and then we're going to have Earth over here. And so in the pattern of the Earth going around the sun, for the Earth to go around and make one tropical year, it is slightly less than it is to do one sidereal year. A sidereal means a star. And so if we track a point that's far away and we fixate onto that point, and we use that as we'll just call it the sub-star point, and we use that as the sub-star point for us to make one cycle around our yearly cycle, to go from sub-star point to sub-star point. That is what is a sidereal year. And that is something that you would need to have equipment in order to really measure that accurately. And, the more accurate, essentially you could probably get some amateur equipment to be able to measure that, but to really get a real fine-tooth accuracy on that, you'd have to really be good with even if you had amateur equipment, you'd have to set things in a certain location, and you wouldn't be able to move it at all. So even something like a millimeter could throw it off. You have to have like a camera in a set location, and it would be best to have objects in the sky, if you're doing amateur work, to be able to have a reference point. And when the star gets exactly back to that precise location again, like within a pixel on your digital camera, that's how you would know it would be a sidereal year. And if you look here, like on this website that I have, and I'll put the link here for the website, a Julian year, they did a simple calculation, 365.25. Well, that's incorrect. And we see that a tropical year, which is essentially what the plants, and I believe that this is what our calendar goes off of, is a tropical year. It's 365.242189, a discrepancy that is there. But you can see that a sidereal year is 0.25636. So it's slightly longer. So again, though, it's only longer. This would be the 5 would be a little over a quarter of a day, and the 4 would be a little bit under, 0.24, 0.25 would be a little bit under a quarter of a day. So if you were to have some amateur equipment and looking at that, I mean, you're only talking a difference of just like a few hours at best. So it's not something that you would necessarily be able to see on your own. However, thankfully, the Creator's calendar, I don't believe, uses a sidereal year. He definitely doesn't use a Julian year. He uses a tropical year that is there. And so on that, let's see if I I got a couple. I got a little bit more time, and I'll get into some interesting things. I had talked about, well, just before I get into that. So essentially, as far as the calendar goes, the beauty in this calendar is that because you're using demarcation points, you're using the demarcation point of a day, the demarcation point of a month, and the demarcation point of a year is that as long as the positions of the hour hand, the minute hand, and the second hand, the hour hand would be like a year, and the minute hand would be the month, and the second hand would be a day. As long as the cycles of a day, month, and year stay fairly predictable, the calendar, it never is off. It's never inaccurate. You don't have to, like with our Gregorian calendar, even though they reset the Gregorian calendar and they only, they basically skipped 3 leap days every 400 years, it's still not 100% accurate. It's still going to get off. It's still going to drift. I believe is the word that they would use. It's still going to drift. It's just drifting less. The Julian calendar drifted a lot. It was drifting. What was that number that I said? I think it was like 3 years every 400, 3 days every 400 years, I believe is what it was, is what the drift is. Well, our Gregorian calendar, it drifts less, but it still drifts. So, what Pope Gregory did is, Pope Gregory, and I'll get in here as we're getting a little bit low on time. Pope Gregory he decided to change when they fixed the calendar. He decided to change when New Year's is. Do I have that up? Let me see if I have that on my website. I believe I have that here. So, and there's a lot of confusion in the calendar leading up into that point in time. Where is that at? I think it's up here. It's called Lady Day. Let me find it. It's a British timepiece, essentially showing that Britain from, I think, the 1200s to the 1700s, they kept their New Year on March 25th. If I can't find it, I'm just going to move forward here. Yeah, that's fine. So yeah, here it is right here. So in the common usage, January 1st was regarded as New Year's Day after Pope Gregory changed it. But in the 12th century until 1751, March 25th, being Lady Day, was the new year. So Pope Gregory, there was a lot of people keeping a lot of different calendars, but most of the calendars kept New Year's in the springtime, like as we see here in the spring equinox. Well, Pope Gregory changed that, and he moved it to January 1st. And a lot of people that were loyal to Pope Gregory changed along with it. But a group of people did not want to change and keep New Year's in the dead of winter. They wanted to keep New Year's in the springtime as they were keeping it. And so they started playing pranks on those people. They picked a day right around their New Year's to play pranks on them, April 1st. And this is the origin of April Fool's Day. And so a lot of, we have the end of the Roman year coming up here, Happy New Year, as people will say, but people don't know that Happy New Year and April Fools is actually a connected period in time. So, connected to one another is that, April Fools, New Year's is still in the spring. You could call them, January Fool's Day. So, Happy New Year's, January Fools, New Year's is in the spring. And so this is why in Latin we have sect, oct, nov, and des. Our calendars today, the September is the 9th month, and October is the 10th month, and November is the 11th month, and December is the 12th month. Yet in Latin, Sept is 7, Oct is 8, Nov is 9, Des is 10. So what they did was when they changed New Year's from springtime to January 1st, they decided not to change the names of the month, which is why our months, Sept, Oct, Nov, Des, September, October, November, December, in Latin says it's 7, 8, 9, 10, but in reality it's 9, 10, 11, 12 because they moved it 2 months back. And people refused to do that. We were called April Fools for doing that. But I'm going to call people that are celebrating New Year's here at the end of this month January Fools because springtime in the scriptural understanding is the new year. So let's get into another point here as we kind of wrap up on time. I usually try to keep it at an hour. I'm going to talk quickly about some flat Earth things with calendar confusion. I'm going to expand on that more. Actually, you know what? Here, I forgot. I have this loaded. Great, we'll do that. So I did an experiment with this understanding that you have here. Or that I just gave, is it's probably best if I do this first. Just give me a moment, because it's best if I show you here. So in geometry, we have triangles. I'm going to do my best to create an even triangle here. It's supposed to be a right angle triangle. That's what that symbol there means. And we are going to duplicate that and shrink it down. Whoop, I don't want to do that. Don't rotate. There we go. Okay. We're going to duplicate that and we're going to shrink it down. So this is the experiment that I'm going to give people to be able to do here. Now, we know that that the proportion of this triangle is different, but you saw me copy it. And so we know that proportionally this triangle is the same. So we're going to say here, we're going to call this little a, and we'll call this big A, and we'll call this little b, and we'll call this big B, we'll call this big C, and we'll call this little c. So the angle here, and we'll call this angle here theta, and we'll call this angle theta that is there. Pen's a little bit small here. Let's do this. And we'll call this angle theta. And so we know that if we have theta here, this angle here is equal to this angle here, because this angle here and this angle here are the same. Therefore, we'll call this alpha. This angle here and this angle here are the same, because the triangles are essentially the same triangle, but they are, one is proportionally smaller. Now, if these two lines here, let me kind of just try to draw here because I can't really point. If this line here, this angle here, and this angle here, if they are parallel to one another, and this line here is also, not that, connected with this line here, so that would mean that that one and that one are parallel to one another. That means that the angle for C, little c and big C, it is coming in the same direction. It's the same angle. So using that understanding, I devised an experiment. And so what I did on the experiment is I took a nail and stuck it in the like in some tape, and then I positioned it where I was located when I did the experiment. It's in like the Fresno area is where I was at. It's Fresno, California. And then what I did is on this globe is I took 3 nails and put them on the representation of the equator. And then what I did, essentially, so that you can visually see it, is you have the big Earth that we are on, and then here's me with this, not to scale, obviously. I put a little globe on the big globe, and then what I did was I oriented them the same so that the angles are the same, so that when the sun, which is in the same location, when the sun is essentially casting its direction of light on Earth, that angle, and it may not look the same here because it's not to scale, but that angle and this angle would be the same. That would be there because obviously the sun is a lot larger than this. But what it means is that that angle and the other angle are the same. And as long as I orient the globe, this model, on top of the Earth properly, I'll be able to get shadow angles the same. And so and I did this in 2020 with a brother of mine. So I put the nails on the equator and then the nail given where I was at. And then I went out in the world, in reality, and I oriented the North Pole to face the same direction as the Earth faces. And so it was a flat Earth experiment, if you will. If the Earth was flat, then the geometry would not work because it would be a completely different shape. The sun would be in a different position, and essentially you wouldn't have the scale would be wrong. You wouldn't have the same angle for the triangles or the same angle for the globe. It would be a different pattern. And so I oriented it properly, and as you can see, and I did this on the equinox, by the way, it's in March, I think March 19th, 2020, I believe is the date that it was. And you can see that this shadow that is here, kind of blow it up anymore. The shadow that is cast by the pole here, it falls directly on the equator. And also this pole shadow falls on the equator. And also this pole's shadow falls on the equator. And not only was it on the equator on all 3 poles, but through time, let's look at the shadow. We'll call it pole A, B, and C. And this pole here up above, that's where I'm at. That's why it's facing up. Pole A, B, and C, we're going to watch as the shadows start to grow longer. Look at how the shadow for pole B is still on the equator, but now it's growing longer. You can see how I'm time stamping them. You can see how the shadow is growing longer, but it's only growing longer. Let's see if I can blow them all up this way. Can I do that this way? Yeah, okay, I can do that. Sorry, I'm trying to get this right. Here we go. Yeah. So you can see how the shadow, how it grows there on all of them. And it's on all 3. The shadow is on all 3. How it's growing for all of them. And that experiment is an experiment that I did that proves globe Earth. Maybe I'll have more time to do it at another point in time. There's a brother that I wanted to share, and he devised a piece of equipment. And let's hear him explain this. And anyone can make this on their own home, and they can find the equinox and the solstice with an analog device, something as simple as this. It's a minute-long video.
To hit the wires yet. So when he hits the wire, on the equinox, it'll be right dead center in this. And it does it every year on the vernal and the autumnal equinox. Now the solstice, this right here.
Here, wait, hang on. Let me reset that real quick.
It hits the
Here we go.
to hit the wires yet. So, but when it hits the wire on the equinox, it'll be right dead center in this, and it does it every year on the vernal and the autumnal equinox. Now the solstice, this right here would be the winter solstice, and this right here is the summer solstice. So anyway, so this wire right here will give me this wire gives me the solstice and the equinox. This wire, it'll cast a shadow right here, and this gives me, like, this will be high noon, and so when the sun comes up, over here's it will give the morning, and this over here is the evening. As the sun travels across. But I mean, it hits dead on. It hits dead on every year, right in the dead center.
And so this here, from here to here, that's north.
Okay, this
north?
is pointing directly at the North Star.
So in the angle also. So you're saying that laser, like a laser pointer.
We laid a laser right here and shot the North Star.
And so the North Star right now is still here.
Yeah, it's right there. That's right. Now, I did adjust it a little bit. I adjusted the pivot this way because on the equinox, I didn't have it exactly to where this would cast a shadow to completely cover this. So I adjusted it just a hair. We were really close. I mean, it would have worked fine. But anyway, I adjusted it just a little bit, and now on the equinox, when the sun comes up, this casts a shadow and it completely covers this. And then once the sun gets up high enough, this right here will cast a shadow dead center in that mark.
All right. So what I want to explain here on that, as we're going to kind of wrap up things, we're kind of getting at the end of time, is what he did is he created a device, and he said that he had to adjust it in the beginning. It took about a cycle to adjust. And then once he made the adjustment, he didn't have to adjust it again, and it works indefinitely as long as it doesn't move. Like, it needs to be a fixed object. And what that is it creates this device, and some people may have a little bit of a difficult time understanding this, but those that understand geometry and they understand mechanical understanding quite well, what it does is it essentially mirrors the shape, or mirrors the pattern of the sun, the progression of the sun, or you could say like the subsolar point or the tracking of the sun, and using shadows, as this thing is essentially, in the one location is facing towards the North Pole, the North Star. So it essentially is oriented the same way that Earth is oriented. So like when you look at where is it at here? When you look at this device, and if you see where my cursor is at the very top there, that essentially represents the poles. So that pole right there essentially represents the North Pole of Earth, and the bottom pole right down here represents the South Pole of Earth. And as far as geometry goes, they are exact. It's the same concept as these triangles. Is that essentially the shape of the Earth is matched by the shape of that device, and it's oriented the same way, which is essentially what I did with my experiment. But my experiment, only you have to pick in order to get the line on the shadows on the equinox, you have to pick an equinox day to do it. But essentially through geometry and having a mechanical understanding of studying these celestial bodies in the sky. A lot of people, they like to do scriptural interpretations only, and I would disagree with that. Not even Daniel did scriptural only interpretations. Daniel he was 10 times smarter than all of the astrologers in the Babylonian school that he went to. He schooled the school, if you will. He was given a lot of wisdom and really brought the Babylonian understanding of the star charts to a higher level. And so today, essentially, we have a lot at our fingertips of understanding, but we don't have to get that complicated. In that, we can do something just as simple as creating a device such as this, and you need to orient it properly. It needs to be like, if you could see here, this, am I able to? I can't. Sorry. That line, makes there's a X, a plus that is there, and then the topmost point, if you can really zoom in, if you have a big screen, you might be able to see it where my cursor is at, which represents the North Pole, and the bottom point, which represents the South Pole. If you're able to get that accurate, meaning that line between the two, the North Pole and that South Pole, if you can get that to be exactly parallel, similar to what we see here, if you can get the little c, the hypotenuse, to be connected to the big C, and you can get those to be parallel, then you're going to be able to have a higher accuracy for the experiment. So when you design this and you orient it properly, and you have this device positioned, you might need to do some minor adjustments through a cycle, but once you have it positioned, those lines on the top of that positioning creates like an X marks the spot, and that X marks the spot will move up and it will move down the base of that device. And when that X moves all the way up, you'll know that it's hit the northernmost point of the Tropic of Cancer, marking the summer solstice. And then when that X moves, the shadow moves all the way down, you'll know that it hits the southernmost point of the Tropic of Capricorn, and that would be the winter solstice. So we don't need NASA. We don't need all of these fancy equipment in order to be able to find the equinox and solstice ourselves. We just need something as simple as two half circles that are mounted on a post, and you can find the equinox and the solstices for yourself. And you don't need to have any fancy calculations for that, and it will be accurate with what the rest of the calendar is, and you'll be tracking a tropical year. As we covered, remember, as essentially the Earth is spinning and the subsolar point, essentially, if you were going to follow the subsolar point, it would essentially like corkscrew around up to the northernmost point, which is what makes the tropic lines, and then it would corkscrew back down to the southernmost point, which makes the other tropic line of Capricorn, of Cancer and Capricorn, respectively. So that is my project. I thank you for getting with me on that and staying with me. I hope I didn't lose anybody. Please put anything in the comments if you have any questions. It is a broad topic, and there's a lot to go over, and there's a lot of things that I simplified, and maybe I'll have time in the future to do some more analysis and some deeper teaching on the matter. But what I really want to get into in the future in the calendar confusion is essentially how the calendar functions, how we make a day, a month, and a year, and then how essentially the whole purpose of the calendar is, well, one of the main purposes of the calendar is to know when the holy days are, when the holidays are. So, it's important that we know when a holiday is, because say, for instance, where like Moses tells everyone, the Passover is in 10 days, and you gotta take a lamb, and on such and such day, you need to put the blood over the doorpost. And if you're like, yeah, I'm gonna do it, but I don't think Passover is in 10 days. I think it's in 16 days, or something. And so, the angel of death, that passed over the houses of the Hebrews, it's not gonna be like, well, they're gonna do it in 2 days from now, or however long from now. But it's important to be doing things on the right time, in the right place, in the right way. And calendar does make a difference. Like, for instance, the 120 in the upper room in Acts chapter 2, Pentecost, Shavuot. If they're like, well, yeah, we're going to keep Pentecost, we're going to keep Shavuot, but we're going to do it, in a week. It's not, today. And so when the Holy Spirit, the Ruach Kodesh, poured down, did someone maybe miss a blessing by keeping a calendar incorrectly, or did someone maybe get a punishment by not keeping a calendar correctly? I think that there are more important things to focus on, but to try to say that the calendar is not important is a gross understatement. So I do believe that it's important to go over the calendar and how it functions. And one of the main reasons is for the holy days. So with that, I'll say, my end sequence that I do is not to cast pearls before swine. I have my jar of pearls here. So I say the pearl of the episode is that we need to make sure that we're not just getting delusional with book interpretations when there's physical things out in the world that we need to that we need to study, especially if these signs in the sky are as important as they are. It's kind of preposterous for someone to claim to have authority on the functionality of the grandfather clock in the sky if they can't even tell you the shape of the grandfather clock and how the mechanics work on it. And there's a lot more on that topic, but that would be the pearl that I would share on that. And so just remember, guard your heart, guard your soul, guard Torah, or pay the toll.